Previously, we have studied truth tables and learned how to write an expression for a truth table using the sum of product approach, and then using the product of sum approach. Now we will learn how to simplify a truth table to write a simpler expression when that is possible. First, we will do it without what's called a Karnaugh map, and this will motivate the Karnaugh map approach that we will ultimately take. Every truth table can be expressed in terms of Boolean operators, and or not. In fact, we've done this two different ways. We've taken the so-called sum of products approach, and we've also taken the product of sum approach. Once we have an expression in terms of and, or, and not operators, then we can build a circuit in terms of and, or, and not gates, and then in turn these gates can be made from transistors, which we will ultimately learn. So if you're going to take the sum of products approach, then each line of the truth table can be expressed in what's called a minterm, an ANDed expression involving inputs and perhaps inverted inputs. And then ultimately we will only keep the expressions for the rows in which the output is a 1. So let us review our basic Boolean operator starting with the not. So in the algebra we have A prime, which will mean not A. And then the corresponding gate will be the not gate, also known as an inverter. It will take a high input and produce a low output, and alternatively a low input will turn into a high output. So in this little circuit we have drawn here, we have the battery, which establishes a low and a high, along with the ground, which is attached to the low. We have a switch that allows the A input to be either high or low. We have the NOT gate, which is that triangle with a little circle on the end. The little circle on the end is really what implies the NOT or the inversion. And then at the end we have a pro, which will indicate to us whether the output was low, if it's not lit effectively, and high if it is lit or filled in with the red as seen here. For the Boolean algebra, we will use a notation where A, B means that the input A and the input B are ANDed. And when two things are ANDed, it is only true when both things are true. Now we are going to be working with electronics, and so we're going to talk about high instead of true. So the AND gate is only going to have a high output when both inputs are high. Our notation for an OR is going to be a plus sign, so A plus B is going to mean A ORed with B. The gate is going to be this sort of rounded triangle. And with an OR gate, the output is false only when both inputs are false. In the sum of products approach, each line of the truth table can be thought of as a minterm, an ANDed expression involving nots and ands, in which the expression is a 1 for that row and 0 for all other rows. For instance, the row with A 0 and B 1 would be represented by A prime B. So the 0 A gets inverted to be a 1. It gets ANDed with the 1 that is B, giving you an output of 1 for that row, and that term A prime B would be 0 for all other rows. This is not yet a truth table, it's just a way to build up to express a truth table. We will then use these minterm expressions to create the overall expression. To do so, you look at the truth table, the outputs of the truth table, and you focus on the ones. Then for those outputs which are ones, you write the minterm expression, which again involves ands and nots, and then finally you feed those expressions into an OR gate. So here's an example. This truth table has 3 inputs, A, B, C, and we write out all the possible combinations of A, B, C. We're putting them in sort of a binary counting order. So we're starting with 0, 0, 0 and working our way up to 1, 1, 1, sort of going from the numbers from 0 to 7. If there are 3 inputs and each can have 2 states, 0 and 1, that will give us 8 combinations, 8 possibilities, and which we can think of as the numbers between 0 and 7. Then the output is different for different scenarios, so this is just sum output. And in the sum of products approach, or the Minterm approach, we focus on the ones. So I put blue arrows next to the ones. Those are the terms that we're responsible for writing. So you take the Minterm or ANDed expression for each row which has an output of 1, and then you OR them. So this is known as the sum of products, because the Minterm, the individual terms like a prime, b prime, c prime, is produced by ANDing, and AND is like a product, sort of analogous to a product in regular algebra. And then ultimately we OR them, or we make a sum of them. So we have a sum of products. And the individual terms that go into making it are known as minterms. So this is also the Minterm approach, or a Minterm expression. Previously, we considered a somewhat extreme example where the output of a 3-input truth table, the first output was a 0 and the rest were 1. So we can take a sum of product approach and we would have 7 Minterm expressions, or we could take the product of sum approach and we would need 1 ORed expression, 1 max term. And so we see that the expressions are logically equivalent, so they're the same logically. The same inputs produce the same outputs, but one is clearly much simpler looking. And then in terms of gates, it will also be simpler in terms of gates. And when actually building it, it's going to involve fewer transistors and take up less space and use less power and just generally save money and so on. Let us look at a few fundamental results from Boolean algebra, and then we'll point out how E and G might play a role in simplification. So capital A represents a Boolean expression. It can be a true or a false. 1 will represent true and 0 will represent false. Plus, again, is our OR, and multiplication is our AND. So the first one is the input A along with ORed with a 1, which is always 1. The 1 is always true, so in anything that's ORed, if one of them is true, it's true. A ORed with a 0 gives you A back. A ANDed with a 1 gives you A, and A ANDed with a 0 gives you 0. So that's the first A, B, C, D. E tells you that A ORed with A is just A. So this is one of the differences between Boolean algebra and regular algebra. Right? This would be 2A in regular algebra, but there's no such thing for Booleans. They're either just true or false. So A or A is A, and similarly A ANDed with A is also A. G is an important one. This says A ORed with A prime is always true. So no matter whether A is true or false, I also have its prime, so I have its opposite. So either A or A prime, one of them will be true, and when I OR them, I will get a true. So that's always true. And then H is when A is ANDed with A prime. That is always false. One of them will be false. I'm going to start with an example that has a lot of simplification, which I'm going to call the trivial example. So here, the A, B, and C are the inputs. I have all the possible combinations, doing the binary counting order from 0 to 7. The outputs are 0, 0, 1, 1, 0, 0, 1, 1. And taking the sum of products approach, I focus on the ones and write the Minterm expression. So that first one was A prime, B, C prime. The next one was A prime, B, C. The third one down there was ABC prime, and the last was ABC. So we start with our expression A prime BC prime plus A prime BC plus ABC prime plus ABC. We note that the first two terms have A prime B in common and only differ by C prime plus C. So I've factored out an A prime B there. And in the third and fourth term, they have AB in common. So again, I factored out C prime plus C. But C prime plus C means I don't care about C. It's either C or not C. It's always true. It's effectively 1. And so I can strike it from the expression and then move down to just A prime B plus AB prime. But once again, I have a common b and can factor out a prime plus a, and that means I don't care about a. So I don't care about c, I don't care about a, and the expression is just b. It's important to stop here and to take notice of what led to that simplification. And what led to that simplification was that we had two terms that differed by only one thing. So if we have a prime b c prime and a prime b c, those two terms have a prime and b in common, and they differ only by c. So when we do any factoring, the factored out a prime b gets multiplied by a quantity c prime plus c. And we know that c prime plus c as one of our fundamental results was a 1. Let's say we have a similar starting point, but it's differed by two things. For instance, a prime b c prime plus a prime b prime c, they have a prime in common, so I can factor out an a prime, but then the parentheses is bc prime plus b prime c. That doesn't lead to any simplification. Let's look at another example and then another possible trick to simplifying. So let's go back to our majority rules examples. So we're going to have three inputs, A, B, C. We write out all the combinations from 0, 0, 0 down to 1, 1, 1. And the logic of this output, again, it's only just one possible output, but the logic of this majority rules output is that if two or more of the inputs are 1, then the output will be 1. Taking the usual sum of products approach, we focus on the outputs which were 1s and we write the expressions for them. So again, these are the rows where there are 2 or more inputs of 1, and we write those expressions. A prime B C plus AB prime C plus ABC prime plus ABC. Without any simplifying, this is what it would look like built in terms of logic gates. So we have three inputs A, B, C. I have not drawn any switches that are determining the state of A, B, C. This is just the sort of logic part. But I have A, B, C inputs. They get all inverted. And then I have four terms, which are three input ands, and then those minterms get put into a 4 input OR gate to finish. Again, recall that our simplification occurs when two terms differ by only one of the inputs. So let's see if that occurs anywhere in this expression. So let me take the A prime B C and see if I can match it up with any of the other terms. If I match it up with try to match it up with the second term, A B prime C, we see that the A changed and the B changed, so it does not have a simplification with the second term. If I try to match up the first term and the third term, A prime B C plus A B C prime, I see that the A changed and the C changed, so it does not have a simplification with the third term. But A prime B C and the fourth term A B C are different only by the A prime, so that will lead to some simplification. Now let's look at the second term. It's A B prime C. We already know it doesn't match up with the first term. Let's look at it with the third term. Well, no, the B changes and C changes. But the second term and the fourth term differ only by B. And the third term, A, B, C prime, does not like to match up with the first or the second, but it also likes to match up with the fourth term. ABC prime and ABC differ by only one term, C. So everybody, the first, then the second, and the third term, would all like to get together with the fourth term, ABC. Well, in logic, we can do this. Because remember, we had a result that A was equal to A plus A. In logic, that doesn't matter. It's not 2A. A plus A is not 2A. A plus A is just A. It's either false or true. And so two times it doesn't make any sense. And here we'll do the same thing. ABC is equal to ABC plus ABC plus ABC. Now everybody has a version of ABC to sort of get together with and cause a simplification. So A prime BC will get together with one of the copies of ABC and will eliminate the A, giving us BC. A B prime C will get together with a copy of ABC, and we will eliminate the B, giving us AC. And ABC prime will get together with one of the copies of ABC, and we will eliminate the C, giving us AB. And here we are showing the logic of that simplified expression in terms of gates. So here's a side-by-side comparison of the unsimplified and the simplified. The unsimplified on the left uses 3 NOT gates, not seen on the right. It has 4 3-input ANDs, whereas over on the right we have 3 2-input ANDs. And finally, on the left we have a 4-input OR gate, whereas on the right we only have a 3-input OR gate. So sort of simpler all around. So now we've seen 2 aspects of Boolean algebra that lead to our simplification. The first is that 2 terms in the sum of products expression, if they are differed by one and only one of the inputs, that leads to a simplification. And the other was that a given term in the expression might participate in multiple simplifications. This was like the ABC term in the majority rules approach. It wanted to simplify with sort of all 3 other terms. These are the 2 tricks that lead to simplification. In our next presentation, we will use an approach introduced by Karnaugh that uses an ordering of inputs known as gray code, and this will lead to a visualization of when simplification can be done.